Hello everyone, welcome back to my YouTube channel. Now in this video, I'm going to show you on SPM physics from 5 chapter 4, that would be detection of radiation. Now previously I've gone through half-life and how to calculate half-life. Now in my previous chapter of radiation decay, whenever you have a radioactive material and decay, what happens, you are going to get active radioactive or energetic particle, like for example in this case of helium. For beta decay you have electron, and for gamma decay you are going to have gamma. Then how are you going to detect it? How are you going to detect that it's a presence of radioactive material? So here you detect the energetic particle. You are not going to detect the element, but the energetic particle. So these three energetic particles can be detected, and physicists in the past have found a way to detect it by understanding nature, which I have gone through it. Then let's summarize it in the following manner. The concept to actually detect, or how to detect all these alpha, beta and gamma energetic particle. Okay, we make use of their ability to ionize the air. Okay, the ionizing effect. Okay, we make use of the ionizing effect. So therefore, if in the event that the air is being ionized, then you can actually make a conclusion that they are radioactive material around it, but you can't tell whether it's alpha, beta, gamma, neither that you will be able to tell what element is it unless you make further analysis. Okay, so you make use of the ionizing effect. Okay, now what is ionizing effect? Okay, so in terms of ionizing effect, what does it mean by that? Okay, put it into a simpler term. So say for example, for the case of alpha, okay, for this 4,2 helium alpha, so what happened because of the huge mass? So what happened when it passed through, when this alpha particle, this alpha nuclei pass through the air, what happened in the air? They're going to have air molecule. Okay, so the air molecule, it will knock off the electron along the way. The electron will be actually being knocked off. Say there are some A molecule here, electron will knock off here and there. You left with only the negative and positive. So the electron will be actually knocked off from the air molecule and left with the positive ion temporarily being knocked off from the atom. So therefore, this alpha would create an ionizing effect to the air, to the path that it actually traveled. So because of this effect, ionizing effect, radiation from a radioactive element causes the ionization of the atom in the air. Okay, how? By knocking the electron off from the air atoms. Okay, so when this happens, then you're going to have this static, actually is floating on the air. Okay, so this is what actually happened. So when this phenomenon is observed, then one could really tell that, oh, okay, so there are some radiation from a radioactive element, but you have no idea whether it's alpha, beta, gamma, neither it is what element. But most probably alpha would be the culprit, because alpha would have the huge mass and the ionizing effect is the highest. So first thing comes to your mind, that would be alpha because of the huge mass. Right? So what are the available tests or available device? Okay, from your reference text, Okay, you should have your reference text with you side by side by watching this video, so that you can actually read through the text. So my video is actually a guide to help you out with the reading. So according to your text, I mean, maybe the arrangement is different from here, but they are in SPM level. Normally they will have the first one, the famous, most universal device, that would be called the Geiger-Muller tube. Okay, Geiger-Muller tube, or in short form, it's called GM tube. Okay, Geiger-Muller tube. Okay, so what's this Geiger-Muller tube? It's actually a small device. From your book, okay? I think you can get this from your book. A small device. It's a cross-sectional view. This device holds the aluminum body that serves as actually the cathode. You have an aluminum body. Aluminum body. Okay. Serve as the cathode, and then it's attached to the housing. Then they are going to have a mica, thin mica window. This is a thin mica window. I'm sure you have your textbook with you, so I'm going to highlight the important parts. This is the mica window. Why they do not use silicon or other window? Because mica allow alpha, beta, and gamma. The ionized air or the electron to pass through it. Okay. So the outside here is actually the aluminum body that serves as cathode, and then you have a tungsten rod in the middle. Okay, so yeah, so a tungsten rod will be connected to the exterior, and then the cathode is actually connected to, it's connected to the counter. So what happened? Of course, this chamber is filled with low pressure argon gas. Okay. So what happened? You bring near a radioactive element. Okay, a radioactive source. What happened? It would actually ionize the air, or perhaps the alpha particle will pass through the mica, knock off the electron from the argon gas, and therefore the positive ion will attract to the element body, and the electron will attract it to the tungsten. Oh, I still haven't labeled it. This is actually a tungsten rod. TG is a tungsten, serves as anode. So anode will attract the electron, so electron will be attracted to anode, and then it's connected to the rate meter. They're going to calculate how many click it receive, and it's subject to a huge potential difference, so you'll be attracted to it. That's, well, from a book is about 400 watt, so you're able to hear a click sound from the Geiger-Muller. So even without the source, you can actually initially you need to calibrate it. So before you start off the Geiger-Muller, you need to first thing you need to make do is actually the background radiation. Okay, background radiation, so that you will not interfere with your reading. So background radiation is actually around us, that you can get it from the soil, okay, or perhaps from the rock. Okay, they do emit radiation, but the doses is very, very low, but they are. You will be able to hear some click, but perhaps in the morning you will be able to hear the cosmic radiation from the outer space, or perhaps from the sun. Okay, they, I mean, from the sun do also emits the energetic particle. So first of all, before you bring in the source to measure anything, you need to calibrate it, switch it on, increase the sensitivity so that it will not count the background radiation. Right? Then so to do that, you need to increase the sensitivity. Okay? To reduce background radiation, so that you will be able to reduce a signal caused by the background radiation. Okay, then that's basically all about it. Then you may want to go through the another 4 yourself from your textbook, but the summary to it would be like, for example, alpha, beta, gamma, alpha, beta, gamma, how I'm going to actually detect it. So characteristic for alpha, huge mass, gamma is just a wave, beta it's just an electron. In order to detect them, Geiger-Muller, or they call it GM tube, Geiger-Muller will be able to detect all 3 of them. Okay, so it's quite universal. If you have Geiger-Muller, you will be able to detect energetic particle. It will be either alpha, beta, and gamma. What happens when you have only spark counter? For spark counter, it measures only the alpha particle. Spark counter cannot really measure the beta, neither gamma. Okay, then next that would be cloud chamber. Now cloud chamber normally comes out in a structure question that you need to actually draw how this look like. So for cloud chamber is also very universal. It's just that in terms of practicability, you can actually bring it out because the setup could be rather bulky as compared to Geiger-Muller, which is actually electronic, like a handphone size. It can be portable size. Okay. Then you can have another way to actually measure it. It's they call agenum bromide film. Okay, instead of ionization, energetic particle like alpha, beta, and gamma is capable to turn photographic film into, to darken the agenum bromide film. So you were able to detect all 3. Right? So and then the 4th one, which normally you were able to see it from the science lab, is called the gold leaf electroscope. I think you have seen one of those electroscope. Something different about the electroscope would be, it looks like, okay, you have a stage, metallic stage, and then it's actually fully insulated from a vacuum small chamber the size of a palm, very small size. And what happened in the middle, they are going to have suspending, a gold leaf. Okay, it's actually made of gold, very tiny gold. Okay, it's not real gold. Not a big mass of gold. So thin, so small, tin foil. Okay, and the middle part is actually a metal stock. Metal rod. Okay. So what happened if you bring near a source, like for example, nuclear? Any radioactive source. What happened? It ionized the air. Okay, and then what happened? The gold leaf will either come close or being pushed away. Okay, but before you bring near the radioactive element, first you need to actually ionize the gold leaf. Okay, so you will either make it positive. So if you make it positive, so meaning you take out all the electron. Okay, first you may want to rub it with some cat fur perhaps. Okay, so you drag out all the electron from here. Then what happened? Similar charges repel, therefore repel. Okay, so you charge it up so that the gold leaf electroscope is ready to detect. Then what happened when you try to bring near a radioactive element? What happened? It ionized the air, remember? So once it ionized the air, positive one side, negative another side, what happened? The electron will be attracted to the allies, the disc, to this metallic disc. Okay, all the electron will attract to it, so therefore you will see the gold leaf will close in the event you have radioactive material. But gold leaf electroscope require really high or really good ionization element. So it detects only the alpha particle. So the rest of beta and gamma, very unlikely you able to see any kind of motion or traction unless the dosage is really high, which is not recommended, and you don't actually use gold leaf electroscope to detect, because it's for classroom display purpose. But for most of the time, Geiger-Muller would be the tool that you use to detect radioactive element, the presence of any radioactive element, by detecting the energetic particle. So I'll leave it to you to go through your textbook to look at how the spark counter work and the cloud chamber work. Okay, so cloud chamber also very much depends on the ionizing effect, and aluminum bromide film. Maybe you will want to Google for the image. How does it look like? I'm not going to edit here. We can get quite a lot of it from a film. It's actually a badge. Perhaps you have a blue color badge on it. Then what happened in the middle? So that's actually a window, and then you have some number to tell the code. You can actually hang it on your pocket or your shirt pocket whenever you get into any facilities. So every month or so, this badge will be sent for inspection to tell the exposure one person will have gone through. So argentum bromide film is actually the one in here, but maybe in some modern case they add some other things because it's not, so that it's not actually affected by the background radiation. Okay, so for cloud chamber, from your book, yes, you may actually go through your book. I'm going to do it here. For cloud chamber, they normally draw something like circle. Instead of circle, you have an image. So what happens if you see straight line emits from the source? You have take straight. The keyword is where take and straight line and almost same length. Okay, almost same length. So that's actually alpha particle. Take meaning you have strong ionizing effect. Straight line meaning you have greater mass, not easily deflected, because 4-2 great mass, so you have a straight line, not easily being deflected. Almost same length in terms of length, meaning equal amount of energy. Okay, so these are the indication that you might actually need it for, you need to write it down for your essay question. Take meaning strong ionizing effect, strong ionizing effect. Straight line means you have huge mass, you have greater mass. Straight line, so not easily deflected. Straight line, not easily deflected. And the same length means equal amount energy. So you may actually gone through beta and gamma. You've gone through beta and gamma. So beta, you have a source, alcohol vapor. What happened? The line is actually crooked. Okay, of different length. Okay, the track is thin. It's thin. The track is thin. Twisted is the word to use. Okay, and different length. Okay, so the ionizing effect of particle is weak because of thin. Okay, therefore it's thin. This is weak ionizing effect. Twisted. Why is it twisted? Because it's continually deflected, meaning you have small mass by air molecule. Different length meaning you have different energy. Okay, so for gamma ray, you can actually guess it. Gamma ray, you hardly see any. Okay, you have a short track, and the track is really thin. It's scattered around. This is one important fact that you should have. SPM is all about keyword. So if you get a keyword right, you can see the track is actually scattered. Short track, thin track, and scattered. This is actually caused by really weak ionizing effect of gamma ray. Right? So these are actually all the method to detect it. So you should actually gone through your textbook. How does it work? You should at least sketch it out. How does it look like? Cloud chamber, tin bromide. But the important one is actually Geiger-Muller, cloud chamber, and spark counter. But actually they are all important, but be sure you have gone through it. Those that I didn't highlight over the video, you should actually go through it, because I believe this is factual. You can do it yourself, but I've highlighted over to you. I hope you read your reference text, and after that you should go through the objective question followed by the structure question. Ordinary, there will be 8 to 10 questions you should go through before you sit for exam for this particular part. And if it is first time watching my video, kindly subscribe to my channel. There are a few more others video available, and I appreciate the thumbs up button. Until then, stay tuned to my next video.